नॉर्मल सेक्शन में ऐसे करना।
हाँ 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 वही करेंगे। हाँ क्या ना
ताकि थोड़ा कैसे मतलब इसलिए मैं कहता हूं ताकि में लगे कैसे नहीं कर रहे हैं वो कब गया Yung tawag na.
Good morning, everyone.
Good morning, ma'am.
Morning, ma'am.
Good morning. We are waiting for the chief guest, that is acting VC, Dr. Manoj sir, to join, and then we will start the proceedings of today's summit. Just wait with us.
मन में था वैसे ही मैं लोग बोला था ना।
बताया पढ़ गया।
Power recharge.
With the divine blessings of His Holiness Jagadguru Shri Shivaratri Deshikendra Mahaswamiji, on behalf of Department of Chemistry, JSS University, Noida, I warmly welcome you all to the one-day International Summit on Chem AI 2026, Intelligent Chemistry for Industry 4.0 and Smart Manufacturing. A very good morning to our respected Vice Chancellor, Sir, Dr. H.R. Mahadev Swami, our Acting Vice Chancellor, Sir, Dr. Me Manoj Kumar, Registrar, Dr. T.G. Mamta Ma'am, Finance Officer, Controller of Examination, distinguished dignitaries, eminent speakers from India and abroad, esteemed faculty members, researchers, industry experts, students, and all the participants for joining us through this virtual platform. Today, we gather to explore one of the most exciting frontiers of modern science, and that is the convergence of artificial intelligence and chemistry for smart manufacturing and Industry 4.0. This summit provides a platform to foster meaningful interaction between academia and industry, encouraging innovation, sustainability, and technological advancement. I am Dr. Ashrima Srivastava, coordinator of the summit, and I shall be your host and anchor for throughout the session today. We thank our esteemed speakers for accepting our invitation and all the participants for joining us today. With your gracious presence, I am confident that today's summit will be both enriching and inspiring. Let us now commence with today's proceedings. May I now request our respected convener, Dr. Roli Verma, to deliver convener address.
My humble pronouns to His Holiness Shri Jagadguru Shri Shivaratri Deshikendra Mahaswamiji. Good morning to Acting Vice Principal Dr. B. Manoj Kumar, Registrar Dr. Mamta, Summit Chair, Deans, HODs, distinguished speakers from India and abroad, esteemed faculty members, researchers, industry experts, students, and dear participants. It's my privilege to welcome you all to this one-day online e-summit organized by Department of Chemistry, JSS University, Noida. We are living in the era where artificial intelligence and Industry 4.0 are transforming every aspect of science and technology. Chemistry is no exception. AI-driven research, smart manufacturing, predictive modeling, and sustainable innovations are redefining the way we discover materials, optimizing the processes, and address global challenges. Chem AI 4.0 Summit aims to bring together leading academicians, researchers, and industry experts to explore these emerging frontiers. Today's distinguished speakers will share their expertise on nanochemistry, digital twins, smart factories, AI for green chemistry, bioenergy, and advanced materials, offering valuable insights into the future of intelligent chemical sciences. I express my sincere gratitude to our respected principal, summit chair, invited speakers, organizing committee, faculty members, student volunteers, and technical team for their dedicated efforts in making this event possible. I also thank all the participants for joining us and contributing to this vibrant academic platform. I wish you all a productive learning. Thank you so much.
Thank you, Dr. Roli Verma, for your inspiring thoughts. Next, it is now my privilege to invite our respected summit chair, Dr. R.S. Jagdish, Dean Student Welfare, Academic Coordinator, HOD Chemistry, to address the gathering. Over to you, sir.
Good morning to everyone.
Good morning, sir.
With the divine blessings of His Holiness Jagat Guru Sri Shivratri Deshikendra Mahaswamiji, it's my privilege to welcome you all to the Chem AI 4.0 Summit 2026. I extend my respectful greetings to our Honorable Vice Chancellor, Dr. H.R. Madheswamy, Acting Vice Chancellor Dr. B. Manoj Kumar, the Finance Officer, the Controller of Examination, esteemed Deans, Heads of the Department, Distinguished Resource Person, faculty members, researchers, students, and participants joining us from across the globe. Today's summit reflects the exciting convergence of chemistry, artificial intelligence, Industry 4.0, smart manufacturing, advanced materials, and sustainable technologies. As industry embraces intelligent and data-driven manufacturing, chemistry is emerging as a key enabler of innovation, sustainability, and technological advancement. A major highlight of this summit is the 6 technical sessions to be delivered by eminent experts from highly reputed academic institutions, research organizations, and leading industries. Their expertise will provide valuable insights into emerging technologies, strengthen academia industry collaboration, and inspire innovative research. I sincerely thank our Honorable Vice Chancellor Dr. H.R. Madheswamy, Acting Vice Chancellor Dr. B. Manoj Kumar, and JSS Mahavidyapita Management for their visionary leadership and unwavering support in promoting such impactful academic initiatives. My heartfelt appreciation goes to the coordinator, Dr. Ashima Srivastav, the convener, Dr. Roli Verma, and all the faculty members of Department of Chemistry for their meticulous planning and dedicated efforts in organizing this summit. I also express my sincere gratitude to all our distinguished resource persons for sharing their participants to actively engage in the deliberations, interact with our expert, and transform today's learning into tomorrow's innovations. Together, let us harness the power of intelligent chemistry to develop sustainable technologies, strengthen industry academia partnership, and contribute to the vision of Atmanirbhar Bharat and Vikasit Bharat 2047, making India a global leader in science and technology and smart manufacturing. With these words, I wish Chem AI 4.0 Summit 2026 a grand success.
Thank you, sir, for your inspiring address and for outlining the vision of the summit. Now, before we proceed to the technical sessions, I would like to present the brief overview of today's summit. Today's program features 6 technical sessions delivered by distinguished speakers from leading academic institutions and industries, each highlighting a unique aspect of AI-driven innovation. We begin with nanochemistry and biomaterial science for cancer therapeutics. This will be followed by the session on digital twins in chemical plants, highlighting the role of digital transformation in industry. The third session will explore smart factories, industrial IoT, and AI integration in petrochemicals, polymers, specialty polymers. And after the lunch, we will continue with the session on AI for green chemistry and sustainable industrial processes. The fifth lecture will focus on AI for energy efficient biothene synthesis pathway. And finally, we will conclude the technical program with the lecture titled From Atoms to AI, Material Chemistry for Next Generation Memory and Computing, which will offer insights into the future of intelligent materials and advanced computing. I am confident that each session will provide valuable perspectives and inspire meaningful discussion among all the participants. Now, may I request all the dignitaries and participants to kindly switch on their cameras for a group photograph. Please keep your camera on for a few moments so that the organizing team can take the good pictures. Okay, so we are done with the photograph. Now we begin with the first technical session of the summit. Our first distinguished resource person of the day is Dr. Murli M. Yalappu, who will deliver a lecture on nanochemistry and interface of biomaterial science for cancer therapeutics. May I now invite Dr. Yamini Pandey to introduce our esteemed speaker and conduct the session.
It is my distinct pleasure to introduce our distinct speaker, Dr. Murli M. Yalappu, Associate Professor in the Division of Cancer and Immunology at the University of Texas Rio Grande Valley School of Medicine and Program Coordinator of the South Texas Center of Excellence in Cancer Research. Dr. Yalappu is an internationally recognized scientist whose research has significantly advanced the fields of functional nanomaterials, nanobodies, and nanoformulations to enhance drug delivery and develop innovative nanotechnology-based strategies for cancer therapy and immunotherapy. Over the course of his career, he has published more than 205 peer-reviewed research articles along with book chapters, which has collectively received well over 20,000 citations, reflecting the broad impact of his work on the global scientific community. His research has been supported by the prestigious funding agencies, including National Institutes of Health, and he has successfully led several multidisciplinary projects aimed at developing innovative nanoparticle-based therapeutics for cancer diagnosis and treatment. Dr. Yalappu also serves as the editorial board of several international journals and is a sought-after reviewer of many leading scientific publications. Today, we have the privilege of hearing from a researcher whose work has helped shape the future of cancer immunotherapy and nanomedicine. I request all of you to please join me in warmly welcoming Dr. Murli M. Yalappu. We welcome you, sir, for the session, and it's over to you for your insightful views.
Thank you, everyone. Can you hear me, Val?
Good morning, Murli Yalappu. So this is Dr. Jagdish from
Dr. Jagdish, can you hear me, Val?
welcome you once again.
Yes, sir. Yes, sir.
Listen to your presentation.
Yes, sir.
Thank you very much.
Good, wonderful. Thank you. Thank you. And I'm
Dr.
sharing
Murali,
my
you are not
slides and
audible.
let me know whether. Are
Sir,
you audible?
you are audible, sir.
No, sir. Sir, he is audible, sir. Audible, sir.
Okay, so can you see my screen, please? Can you able to see?
Yes, sir. Yes, sir.
Okay, so good morning, everyone. So this is Murali
morning,
Yellappa. I'm
sir.
associate professor and director for immunology and microbiology division, and also coordinator for seminar series here with the University of Texas Rio Grande Valley School of Medicine. First of all, I welcome everyone for this wonderful summit, Chem AI 4.0 Summit 2026. And I'm glad that I have been invited for this meeting to the university dignitaries, and also the especially Dr. Jagdish, who invited me to join for this meeting. And I'm glad that you all arranged my talk in first in the morning at your place, but for me it is 11:30 in the night. Okay, so hopefully I will do better. I will convey the message what I want to do. So simply, I want to hear. Can you see the slides? Those are moving.
Yes, sir.
Yeah. So
Yes,
you
sir.
all see my slides are moving, right?
Yes, sir.
Yes,
Okay.
sir.
Yeah. Sorry. Yeah. Sorry. So I want to introduce the nanochemistry to all of you this morning, because the nanochemistry, it takes fundamentally right from biomedical applications to even the rocket science, where you can make very composite material. Those are like very strong in mechanical properties. At the same time, in some of them are very soft material you can even use for in electronic applications, sensing and so on. So the chemistry plays a major role in devising all those materials such a way that the same material can be applied for wide variety application by combining various way of making those materials. Simply, today I will be primarily dealing with the biomaterials, those mostly used for cancer therapeutic applications. So if you see on this slide, on the top of this slide, you will see such a small molecule from glucose, protein, viruses, and cell to even tennis ball. Where you see like small molecules, they do have a 10 to the power of minus 1 nanometer in size, but whereas in the proteins, like 1 nanometer, DNA is 10 nanometer, viruses, those will be falling 100 nanometer in size. But when you see any living cell, it could be ranging from a couple of microns to 100 microns also. But when we talk about nanomaterial, those primarily today dealing with the 1 nanometer to 100 nanometer. Why? Because they have a specific feature that we can employ for cancer therapeutics. When we talk about nanomaterials, particularly for drug delivery or any other microRNA, siRNA, or any viral delivery, including your COVID vaccine delivery, like mRNA delivery, right? So all those things can be uh, formulated with various type of nanomaterials, primarily to increase the solubility and to minimize the systemic toxicity and to improve the bioavailability as well as PKPD of those molecules or microRNA or any other macromolecules. At the same time, in the case of cancer therapeutics, it can be improved its targeted efficacy when you use nanomaterials. On the other hand, you can also introduce some of the reversing the drug resistance mechanism when you apply some of the nanomaterials. So why this is happening? Because these nanomaterials, when you see in the bottom of this, slide, you can see the, you can see here, like, hypoxic condition where, free drugs, they cannot penetrate deeply into the tumor, whereas in the case of nanomaterial, they are able to go inside and then do its therapeutic activity, whereas free drugs or free molecules are not. At the same time, when you talk about drug resistance, in this case, for example, docetaxel, it is widely being used for various prostate cancer therapeutics, and you can reverse all these various drug resistant mechanism right from the angiogenesis or various other mechanisms, including activation of REGF pathways and so on. Simply, if I say nanomaterial, you will be imagining that, how they look like, in your brain, right? So you might be thinking like, simply you can see some of the, chemistry based on the, very smart nanomaterials you can make from 1 to 10 nanometer. Primarily, those are dendrometer or metal oxide or carbon nanotubes. On the other hand, whereas the other material, primarily polymeric or lipid-based formulations, those falls from 10 to 200 nanometer or 100 to 300 nanometer, primarily, nanogels, polymeric micelles, lipids, and various other nanomaterials. At the same time, you can also go with some of the microgels or, or macrogels, where you can use for similar kind of delivery applications. So when you see about the other materials, like, here, why we want to use any drug delivery application, these nanoparticles, because they obey the passive targeting, meaning that, if you see this pictorial here, you have a nano formulation. When you pass through into the bloodstream, these nanoparticles keep going, circulating into the bloodstream, where they can be seeing some of the leaky vasculature that is present only in the case of tumors. So through this leaky vasculature, these nanomaterials go into these tumors and they lock up there, and then therefore you may seeing the lot more amount of the drug accumulation into the tumor compared to any other organs. So this is called passive targeting, whereas the active targeting, meaning that, all the nanometal, they keep going, but once they obey the EPR mechanism, that is nothing but passive targeting mechanism, where these nanoparticles, they have a specific ligands onto these nanoparticles, where they specifically recognize the tumor cell specifically, because of, like, they might be presenting EGFR or various other, HER2 or various other formulations. Okay, so I don't see this. Okay. So when we talk about nanomaterials, you might be imagining whether those are spherical or maybe a rod shaped or any other geometric, like it can be a, pyramid shape. You can create all those by employing various chemical methods or various physical methods, and you can see that, each nano particle size or geometry, it plays a major role in the deciding what kind of delivery, that mechanism that we want to explore, as well as its zeta potential also having some role, and including the hydrophobicity, hydrophilicity of the surface modification, and the active targeting might that you put it on the nanoparticles, right? Well, once you make the nanoparticle, where they end up at the end, right? So if we inject anything into this in a human body, they will be cleared out by various mechanism. Either it could be cleared by renal clearance, or, by the, liver, like when they have a 1 nanometer to 10 nanometer. Whereas you have a nanometer like 10 nanometer to 200 nanometer, those are a very good formulation that where you can use for therapeutic application, particularly for cancer therapeutics. So considering all these, like, there are so many different type of nanomaterials people have been made since like 1800s. For example, like, iron oxide was the first synthetic material that was made for uh, human MRI imaging applications. You can see various other gold nanoparticles, silver nanoparticles for antibacterial application, and various antibody drug conjugates, and various other nanomaterials primarily developed during the 19th century, later 19th century, and close to 2000 year, like now you see more advanced materials. Those have been developed for various therapeutic applications. And I want to give you a 1 minute on this slide, because you will see that one of the drug called aspirin, it's a pet, it's a trademark for the acetyl salicylic acid, where this was synthesized way back in the 18th century, 1887, but the same drug still being consumed by majority of the human being on this planet. Okay, so but the same drug is being you know delivered to the human in various methods. Like earlier it was some kind of different older formulation. Now the same, like microparticle formulation of that molecule is being widely used for, because it can be increased 10 times more potency of the same molecule when you make them sodium carbonate based nanomaterials. Okay, so here are some of the examples that you can see and appreciated by some of the approved, every approved agents for chemotherapy applications in the case of cancer therapeutics. So I want to give a minute on this slide, where you see doxorubicin is a very potent molecule for various solid tumors, including breast cancer, ovarian, and GI cancer, and also some of the hematological malignancies such as lymphoma and leukemia. So the mechanism, I don't want to go to the biology into it, but this molecule is very toxic to the heart or smooth muscle cells in the heart. Okay, therefore, whenever this drug is prescribed for any cancer patient, along with this drug, there is another pharmacological agent being used to reduce the cardiotoxicity of this particular drug molecule. So being using like another pharmacological agent, people thought that early 1980s or 1990s, like the same drug, when you put the drug into the liposomal formulation, that is like doxil or doxorubicin and a HCl liposomal injectable formulation, where you can see complete absence of the cardiotoxicity when you make the same drug in the lipid formulation. Considering the same technology, ambisome is another formulation developed later after doxorubicin, like for anti-fungal applications. And another drug molecule I want to discuss about paclitaxel, it's widely used for ovarian, esophageal, lung, cervical, and pancreatic cancers. Its mechanism, like again, it stops some of the proliferation of the cells or the cell mitosis to apoptosis pathway. So what the same drug, earlier, like Cremo 4EL, like where it's a wax-based formulation, people have been used, but it has a lot more adverse reactions, where you can improve such adverse formulation by simply formulating into a nanoparticle. Here in this case, high human serum albumin conjugated paclitaxel. So there you can see that more amount of drug is being delivered at the tumors, and also you remember that we called as like EPR mechanism and active mechanism. Luckily, this formulation obey both like EPR as well as the active targeting mechanism by identifying some of the protein called GP60 or spark proteins that are highly present on the tumor cells. So same way, the same technology can be applicable for various other molecule. Here in this case, PLGA based lupride acetate formulation where it is called Eligard. It is being prescribed for prostate cancer therapy for as a depot molecule. Like you inject this drug, it can work for 1 month, 3 months, 4 or 6 months, based on the amount of drug in this formulation. You inject once and then you leave it, and then it is very active for up to 6 months depending on the formulation. And even like some of the iron oxide based formulation itself active in treating some of the kidney chronic kidney diseases and some of the anemia. At the same time, the same technological molecule can be used for hyperthermia application. For example, here, like we employ some of these nanomaterials for brain related tumors. Like you can glioblastoma, you can treat with the hyperthermia methods, right? So these are all well, like the applications that we can learn, but at the same time, these all the nanoparticles may not be applicable or may not be suitable for some of the formulation, like earlier formulation of Feridex, like it's a iron oxide based formulation. But if we keep this formulation on the the storage condition, like those will precipitate and you cannot no longer inject that into the human. That's one drawback. Like therefore, that type of formulation has been recalled. And another one is like not necessarily you want to give like better chemistry on these nanoparticles, but some of the times, like too much chemistry is also negative. Like in this case, for example, like wind formulation, where you see the lot more like conjugation of the PSMA targeted peptide on the surface of these PLGA based nanoparticle loaded with docetaxel as a drug. But at the end, like this has been failed in the phase 2 level, because when you use this versus its precursor drug molecule, the payload at the tumor side, those were same when you try with the human clinical trial. At the same time, like another molecule, like it has been not very successful. Keeping in all this in mind, like we here at the UTRGV, like we have a some nano mission, like funded various programs. Like it was like 2.5 million for separate, and then we had our own separate funding up to 6.5 million for as a center. And we also received 2 years ago like an 18.5 million dollar for developing the nano center, where I lead a major role on the developing the research capacity core. Okay, so we started way back on this research. Simply I want to explain you one of the process how we develop various type of nanomaterial. You see that like here, for example, like so where you see this, like here, this iron oxide core where you can precipitate it by combining the iron 3 iron 2 salts. In the presence of ammonia, you will get some of the iron core. And if you leave iron core as such, that is not very stable in nature. That's why you have to give some stabilizer. So here we purposefully we coated with some of the oleic acid layer in the beginning. Then later on, we again gave another different type of layer that has a PEGs of different chain length, like 2000 molecular weight, 4000 molecular weight, and even more higher, 8000 molecular weight, and which has a active functional group that can be conjugated to any antibody or aptam or any other. Okay, so we optimized this, and then we received a patent in a way back on this material. And considering this material, like we developed a lot more formulations. Okay, this was our basis that how we can develop, right? The same material later on we replaced with some of the other advanced material, like rather than folic acid, we replaced with some of the cyclodextrin and some of the other type of materials where you can load more amount of the drug, okay, while keeping that antibody conjugation capabilities. So here I would say one of the example, like how we would do any study, like we'll create some of the nanomaterial. Here in this case, PLGA nano formulation. You see that we characterize by TEM, dynamic light scattering, and also we'll check the uh, nanoparticles coming into the cell when we incubate into the cancer cells over time. Like 0 time, you don't see anything here, but whereas in 1 hour you see some of the particles, 3 hours there are more accumulation, and 18 hours those are very close going to the nucleus of the cell. Okay, and then you see the more vacuolization formation indicating the cell is undergoing apoptosis. Okay, apoptosis nothing but those are going to die very soon. The same information will be evaluated by various methods, like some of the animal studies, some of the cell culture studies, where you see its activity, it is increased when you have formulation of the drug molecule. Here in this case curcumin compared to free curcumin, you will see the more efficacy here. You see more band means like more apoptosis here in this case. Same thing we know will confirm by some of the immunohistochemistry. I don't want to getting too much bored with the biology, but that's what we do, like various other experimentation. Our chemistry would be the first slide always, how we will make them and how we'll confirm, but all other things would be biologically proven in the cellular culture or maybe in the animal mouse models. Okay, the next one is like same technology can be implemented for not drug molecule but also can be used for the molecule called microRNA. Okay, so microRNAs, like some of the microRNAs are absent in certain type of tumors. Okay, so in this case, like if you deliver those microRNAs through nanoparticle, maybe you will see better effects. So that's what this our first slide, first figure. I always tell you, like that's a chemistry. It is involved here. We develop and then we conjugate with the molecules. Here in this case, microRNA 205, where it is absent in the prostate cancer cells. Now we will be seeing and confirming delivering of these and having the activity in the culture models, and then testing on the various other mouse models. So this is again busy slide in a way, how we create a different type of nanomaterial. Here you will see what we did here uniquely. We self-assembled paclitaxel with some of we tested like close to 20 different ratios of various polymers and so on, and we end up having the polyvinyl pyrrolidone composition, and coated with some of the cellular clocking on these nanomaterial, and then confirming that one of the material like here we saw that very more amount of the drug going into the tumor, that you will see here more accumulation here in the tumor compared to all other type of material. Okay, so this is happening not just because of like not only the particle size but also the chemistry that you have been implemented on this surface of these nanomaterials. Okay, this slide where we are showing some of the self assembly of not one drug but dual drug here, gambogic acid, as well as another drug gemcitabine, using two formulations like human serum albumin, tannic acid, cross linking, and then again you know later time point, first slide would be figure would be our chemistry involvement, and then then confirmation with the various biological assays, in the animal mouse models and so on. Finally, our goal is here, you see our formulation, it reduce the tumor growth, compared to the control mice. Okay, here you see bigger tumors here, and when you treat with our formulations, the tumor size went very low. And on the other hand, maybe you can also say the tumor did not grow when you treat with this type of materials. Well, you may be knowing this or maybe not, but in the case of cancer, like if different parts of the body, they produce different type of tumors, like breast cancer, it is developed in the breast, brain cancer, it develops in the brain, you know something like that, right? But at the same time, once the brain tumors or breast cancer tumor or any tumor that is primarily originated from the same organ, that can go and circulate into the blood cells and then go into the different part of the organs. For example, like breast cancer, it can go to the bone, and also the breast cancer can also go to the brain. There are so many other something like that. Colon cancer can go to the liver, can also go to the bone, can also go to the brain. Okay, so that means, like you can also develop some chemistry where it can specifically, your nanoparticle can go to the bones as a bone metastasis model, right? So we develop some of those, like you will see the blue color means like more binding with the bone type of material, here in this case mouse bone. And we develop some chemistry like where you conjugate some of the self assembly based molecules with the zoledronic acid. It has a tendency for the bone. Okay, so same way, like in the tumor, we always think that tumor means only it contains the tumor cells, right? But in reality, tumors might contain a lot more immunological based cells also. For example, macrophages. Okay, so macrophages usually primary role would be like if they see any foreign particle, it will take out and then it kills. Okay, but when these cells goes to the tumor, the tumor machinery, they hijack the primary function of these macrophages, but they turn out to be, they will be helping to the tumor to grow further. Okay, so in that case, like tumor cells may have up to 50% of the macrophages type of cells. So that means, like if you can generate any formulation that can bind to the macrophages, that also beneficial, because like you will be delivering more drug, right? So here with that concept, we generated some of the macrophage targeted formulation by changing the some of the core nanoparticle with the tannic acid plus some of the mannose decoration on these nanoparticles. So simply, all these, like it will be giving us some information that you can modify the surface morphology by using various chemistry method, various self-assembly method, various conjugation methods. But our primary goal would be delivering more payload at the tumor site. And at the same time, like you can also implement some of the nanomaterials, like nanofiber, loaded with various other or therapeutic molecules, and again you can see better therapeutic efficacy. Okay, so without further ado, like these are the chemistry concept that I want to introduce here. I'm sure that you will be gaining some knowledge of these, and then can be applied some of the AI concept. For example, like why nanoparticles, different particles can go into the different extent into the tumor, uh, tumor spheroids. Tumors, like they don't allow the drug to be penetrate, right? So you can implement the AI, like generating like vast amount of the, for example, like here you see cellular uptake data, or maybe how they work with the cellular loading, or maybe the activity of the various nanomaterials, like here in this case proliferation assays, like you do 100 different type of proliferation assays with multiple drugs, and then put it into the AI, and then AI can give you a model. Okay, so this type of formulation, if you make it, if you alter this, maybe this will be penetrating better, and you will be able to implement the therapeutic benefits better. Some kind of AI, it can be implemented by giving such kind of information for both AI and ML methods. And one of our faculty is highly dedicated to implement those kind of methods in our division. And and maybe in the future, like we will be coming up with the new way of testing the same nanomaterial when we apply various nanotechnology based approaches for and dissecting some of these mechanism. And I would like to thank like various funding sources that we have, and our team, and our higher education team, like all our faculty, and other administrators. And this year we had done a uh, symposium at the South Padre Island here, so we had close to 300 uh, people attendance on, not online, but it's a physical meeting. Like we had like 3 days meeting, and we are glad that we were able to successfully conduct. And in the future, if your college is interested, maybe we'll give some opportunity to participate via online for this meeting. With this, I want to stop here. I took 1 minute extra of your time, and I'll be happy if you have any questions to if you have, or you can also come up anytime. If you have questions, reach out to me, and ask any type of questions via email also. Can you hear me?
Thank you so much, sir. So we are having few questions.
Okay, yeah, please go on.
One of the participants have asked that why was PEG chosen as the coating material in this study instead of silica or dextran?
Yes, so you can use multiple. Dextran is a very high molecular weight. Okay, and PEG, like you have a different type of small molecular size. And also you have an opportunity, just you can conjugate at the end of the PEGs with the NHS molecule, like those are readily available. That is, the NHS molecule is highly reactive with the primary amine for any antibody, optom, or any other biological conjugations. Okay, but there is no wrong in choosing any other surfactant agent, like dextran, or silica. Silica being used widely used, but silica requires a different chemistry to stabilize the its surface. And yeah, it's like it's a where you apply. Okay, so we are using like this small molecular weight. It doesn't increase the nanoparticle size. Okay, that's what we want. Like we don't want to have big molecule that will take up more space of the nanometer size.
Rosie, I hope your query is now cleared. So the
Yes,
next,
ma'am. Yes, ma'am.
okay, so the next question that we have is, if we increase the coating thickness, will it reduce the magnetic response of the nanoparticles prepared?
Yes. So whenever it's not only the surface chemistry, but also the particle size, core particle size also has a effect on the magnetization values. Okay, and smaller to bigger, they have a different type of the magnetization values. but certainly more amount of coating will automatically reduces your magnetization saturation values, meaning that if you want to apply for any MRI applications, it would be, you might need to be use like a lot more amount of the iron oxide based particles.
Thank you, sir. So the next question is that how are gene editing tools integrated with the nanoparticles for the drug delivery system?
Yeah, I think the CRISPR Cas type of knockout things is widely implemented in recent days with the various other type of nanomaterials, but at the same time this only the delivery vehicle, but it doesn't increase its activeness. Okay, but only it's a kind of carrier for those tools, like when you do the CRISPR knockout and those kind of things. But if people use different type of nano construct, like for example, like mRNA vaccine, like it's like the best example that we can come up. And in our lab we are also doing some of the some of the plasmid transfection with the various other nanomaterials or nanoconstructs. But it's often struggle with various type of cells, and how much we can give and the birth ratio. We need to optimize for different cells, different ratios, so that you will be getting very optimal values.
We have two more questions with us, sir. So what
No,
are the
no
major
problem. Please go ahead.
challenges? Okay, so what are the major challenges in translating nanoparticle research from lab level to the actual physical level where we are actually using them in?
Right, and it's like it's very, so whatever we do in the test tube or in the beaker, translating into the, I'm not going into the human studies, but developing the batches itself a struggle. Okay, but if you're lucky, if you can make all those things. But again, like you do in the studies such as like cell culture and mice model, or maybe in the rat model, or pig and dog models, your concepts are well uh, received in those models. But even though like there is no guarantee that it will be replicated into the human studies, right? So the if you are applying for cancer therapeutics, each cancer, it has a lot more its own heterogeneity, right? So within the like same type of tumor, like I'm talking about broadly breast cancer, prostate cancer, right? So even within the breast cancer, there are 20 different type of breast cancers. Okay, and whenever you apply for any approvals, you go with okay, in the breast cancer I would be applying for this type of breast cancer. Okay, if you go broadly, none of the drug is going to work out for all type of breast cancers. Okay, so those are all, it's good that we can test them, but it's very difficult, like the molecule that you make, you know it depending on the molecule that you have potency, not the formulation what you have. Okay, formulation always going to be helping the molecule what you have, like the drug molecule or whatever it is, we can modify in a different formulation to increase the its pk pd, or maybe it's a more amount of delivery at the tumors, right? That's all we can do it, but we don't know that whether that is sufficient there when you go for the phase 2 and phase 3 trials. Okay, if there is a only marginal increment, then there is no point of translating that into the human studies, right? So that's where all the struggles come up with.
We have one or two more questions, sir. Since AI is the hot topic right now, so one of the participant has asked that even before we synthesize a nanoparticle, can we use AI and predict their properties and their behavior, how they'll be behaving in a chemical reaction?
Right. And it's fascinating that earlier, you see all my cover pictures. So on the first page, right? So you see these pictures, these we used to struggle to make these kind of things, and for this, we hired a person to make this image. We paid $2,000 to do it. Okay. Now the same thing I can do with $0. Okay, because of AI. Okay. So all these, to make all these, for to make all these, we spend, each, at least we spend from somewhere, 500 to up to $2,000 to make one of these. Okay. Only to make these. I'm not talking about the publication of these cover art. Okay. So now the AI is having a major role. Okay, it's if you have a data, there are, if you put in the PubMed or elsewhere, where you see a lot more publications that you can find out, elsewhere, or maybe the Valley Interscience. But we often use PubMed. It's for biology applications. We always go and search in the PubMed. If you go into the PubMed and then you derive the data, you put the in the PubMed, cellular uptake, and you give the PLGA polymer, and then different, particle size, a different morphology, different, surface coating, and different, might is added, and then see, and then feed the data into the AI. Okay, the uptake was this much, and then the activity was this much. This drug is better, that drug is better. Then certainly you can get to some information. Okay, but not necessary that would be true or not. But you need to again verify by experimentally, right? So I was watching on the Facebook or somewhere, somebody was asking to the AI, hey, this mushroom, is that good, is that toxic or not? AI say, oh, don't worry, it's good, you can consume. Okay, then the person will consume and then he is dead. Okay, so then AI say, oh, it's my bad. Okay, it's my bad, now I know it is toxic, and can I give you another answer? Okay, so it that bad, in some cases. But a majority time you can take the AI help, and use it, and then you verify, and then you implement it.
So we have lot many questions, but because of the time shortage, I think we'll have to move on to the next session. So can you please share your email ID so that all of them can ask you the questions directly?
Right. Can you see my main screen, that the ETRGV? Are you guys able to see that or no?
Not right now, sir.
You are seeing?
I can see you.
So that's where my email is. It's
You can type it in the chat box otherwise, sir.
okay. Okay. So okay. So can you see my slide now?
No, sir. Still, we can't see the slide.
Oh, you cannot see. Okay. Okay. So that's fine. So I can just type. Yeah. Okay. But if any faculty wants to talk more about it, I will be available any other time. We can put another meeting. Uh, we can discuss, like, if anybody looking for collaborative opportunities, those
Sure, sir.
I can help. Okay.
Okay. Yes, sir.
Right. So I put my email ID, and then I think Professor Jagadish. I think he has my phone number, and if any faculty they want to have a good conversation or any collaborations, I'll be happy to help. Okay.
Thank you, sir. We have received your email ID. Thank you so much for such an insightful session and sparing your time and giving us your depth knowledge of the topic. Thank you so much, sir.
Yeah, no problem. Thank you. All the best for the rest of the meeting, and then it's already 12:15 for me. It's early in the morning. I'll go and sleep, and good luck everyone, and thank you, sir, for the invitation, and hopefully I'll be talking to each one of you down the road. Thank you.
Thank you, Dr. Yamini. Now we move to the next session, that is the second session of the day. And we have with us Mr. Bhuvnesh Sharma. The topic of his lecture is Digital Twins in Chemical Plants. I request Dr. Kirti Srivastava to introduce our distinguished guest and then take up the session. Over to you, Kirti.
Madam, we are not getting your voice.
Good morning, everyone. It is my great pleasure to introduce our esteemed guest speaker, Dr. Bhuvnesh Kumar Sharma.
Madam, again your voice is muted.
Ma'am, your voice is not.
Ma'am, voice is not coming?
Now it is okay.
Voice is not coming.
Okay. So you have to be a little louder.
So, Dr. Sharma has extensive expertise in pipeline diagnostics, intelligent inspection technologies, and asset integrity management. His work is focused on integrating cutting-edge technologies such as digital twins, artificial intelligence, and advanced data analytics to enhance the safety, reliability, and operational efficiency of industrial infrastructure, particularly in chemical and process plants. His contributions have earned international recognition, and he has proudly represented BTT Pipeline Integrated Solutions at prestigious global innovation platform, including Biotech France. He actively collaborates with industry, academia, and government organizations to promote indigenous technology, development, and innovative engineering solutions for the future. Today, we are privileged to have him deliver an expert session on digital twins in chemical plant. I'm confident that his vast industry experience and practical insights will provide all of us with valuable knowledge and a deeper understanding of this transformative technology. On the behalf of Department of Chemistry, JSS University Noida, I extend a warm and heartfelt welcome to Dr. Bhuvnesh Kumar Sharma. Sir, we are truly delighted to have you with us, and we look forward to your enlightening session. Thank you, sir, and welcome. Over to you, sir.
Thank you, madam. I hope everyone is having my voice as of now. So there is no technical
Yes, sir.
glitch.
Yes, sir. Yes,
So,
Yes, sir.
perfectly all right. Thank you. Thank you so much. my name is Bhuvnesh Sharma. It is already being described by Madam, and I'm not used to be from the fraternity from the professors. I used to be the fraternity from the industrial. Uh, uh, I can say that these are industrial server to the country. So we are one of the, as our Prime Minister says, themselves saver. So we are also a saver for this country. So and for the humanity. What we actually into? What we actually into? We are into oil and gas. Everyone has oil and gas at their home. आपकी गाड़ी में oil के लिए everyone is going for run their vehicle and to the petrol pump and gas station, and even the gas is coming to your home for making the food and other things. So I think that everyone is aware about oil on gas. Are you aware about it?
Yes, yes, sir. Yes.
So tell me, I wanted to be this session not to be a putting my knowledge on you. I wanted to interact with you, number one, and with the interaction, my message will be passed. That is for sure. So I would love to be interact with the people, and if every one of you can come with a video or can on your video, that will be great. Can mute your mic, and whenever is required, yeah, just open it. So everyone will be. I request everyone to be open your video so that I would be able to see. Thank you. Those who didn't did, please do. Thank you. Uh, 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 this is a morning time. Somewhere it is a night time as well. So everyone having water at their home. Everyone having water at their home in your bathroom and other for the other utilities.
We are in institute, sir.
The institute is in institute does have water or not in washrooms?
Yes.
And for the drinking purpose and other things, I think yes.
Yes, sir. Yes, sir.
Tell me, if the water pipeline is coming to institute is got leakage, what will happen? If there is a pressure inside, less pressure inside, the dirt will come inside as well. And if there is
Yes,
high pressure inside, the water will blast and it will be on road. So this is a kind of integrities we need it to be checking off. If we are getting the dirty water for our food, then that can harm a society actually. So it is for the water. Once this happens with your gas pipeline, then if it has happened with your gas pipeline, which is coming to home, which is coming to the institute,
There will be a danger of accident, sir, explosion.
which type of accident it is? It is a small
Fire hazard, but the fire hazard.
fire hazard. You have the cylinder at your home.
No, pipeline is there.
Pipeline is there. If the pipeline is leaking at your home, what will be your next action?
I'll switch off that point. From there the gas is coming.
Is still the wall will leakage then?
Then we'll use fire extinguisher.
Fire extinguisher, very good. And are you have the fire extinguisher at your home?
Sir, we have fire safety valves in our society, so we
And
can
if
use
the
that.
pipe, okay, and if the gas is continuously coming and it is not stopping, then how you will be
We
taking
have
care of?
to come out of the house.
Sir, we can stop the connectivity between environment and that pipe by using cloth or by some material like plastic that will be available at home, or tape. We can cover that point so that they can never come in contact with environment.
I'm very happy that everyone is trying to justify for the small 0.5 bar pressure pipeline, that how to stop the pressure from, how to stop the hazard from the 0.5 bar. The pipeline is coming to your home, it is 0.5, but the pipeline is coming to Gujarat to Delhi, it is 120 bar.
Yes, sir. Yes.
And if something happens with that, the 1, 2, 3, 4, 5, or more than that, these number of villages can be burst out. So that's why we are focusing on. Initially, it happens. Still, this is happening. Just now, one
The
accident is
video is
happened.
pausing.
Are you okay? So just now, the things is being happened in one of the toll station, the one LPG tanker blast. That was the small tanker. Once you see about the plants, there are a lot of tankers can fill from a plant. So this is a danger can be taken. This is the danger can happen if you do not have a real scenario of your plant in front of you. I would love to showcase you something. It is not like that I'm going to present a normal PPT to you, but it is just like a overall where it is. One second. So are you able to see my screen?
Yes, sir.
Great.
Yes, sir.
Great. So initially in ascent age, when there was no sensor and there was no AI, what the people was doing, there was some mechanical stuff was there, and we was burning the crude oil and making the crude oil in different parts. Different parts means the different parts is belongs to petrol, diesel, kerosene, even the crude. That road is having the black color uh, charcoal. So that type of charcoal is being coming from the crude oil only. Even the plastic is coming from crude, and there are a lot of other substances are coming from the crude oil. So what was we was doing that we was burning that particular crude oil and on a high temperature, and in different temperature we was getting the different product from that particular crude oil, and we was collecting that particular product and sending those product to the required place like Delhi, Bangalore, and everywhere else. So uh, but the integrity of these plants, if the something happens with this particular plant which is supplying the things to the Delhi, what will happen, madam? Hello? If something happens to that particular plant which is extracting the petrol from crude oil, if some pipeline is being leakage, what will happen?
There will be blast.
But
Blast and-
the blast is a small thing. The supply to the Delhi will cut off.
Yes, sir.
And how you will make the food for your children's.
Hmm.
So this is where the digital twin come in picture. Initially, it's called SCADA. We was having multiple sensors on multiple places wherever the risk is, like pressure sensor, like temperature sensor, so that the things can tell us that what is happening with their particular health. Pipeline health is also very necessary to supply the things to the required place. So like some anomalies there, corrosion is there that can be identified before it will blast. So our supply can be continued to the particular place where it is going as of now. So these pipelines are normally buried. Even the most of the structure are buried. Buried, I mean, it is underground, so nobody can see it. So now you will see it. You can see through the sensors only. So, and these pipelines are the lifeline of the country. The lifeline means these pipelines are the lifeline of the country. I can what is the lifeline? It is the bloodline actually. If this line is being stopped, that particular area is being cut off. Just now there was an incident happen with Indian Oil. Uh, uh, we have a river here in Delhi that called Yamuna River. Yamuna was on flood, and one pipeline was passing through that particular river, and that pipeline is being cut off. There was two area in Panipat was not did their work for 3 days. So it is a loss of the country. So once you, that's why the digital twin come in picture. I'm not particularly focusing on my slide. I'm just saying that what the slide wanted to be say. So we can with the digital twin, once we have the multiple sensors on the at multiple places. Are you able to see my slide, right?
Yes, sir.
Okay, the changing of the slide is also there.
Yeah.
Perfectly all right. Thank you. So once you have the live data of your plant, the live data of your plant, of your pipeline, you go to that taking the decision, like we have a corrosion of 90%. 90% means the 90% pipeline is being corroded. Only 10% is remaining. What pressure we need to give to the pipeline so that that particular pipeline can run another 6 months, and that particular area can be taken care of by the engineering stuff and other things. So even we can repair it actually. That's a kind of repair is a good word for to understand as of now. So these live data tell us that where we need to take an action immediately so that the supply can continue. For that, what we actually do, it is not only the putting the sensors. The sensors was putting around 30 years before when the SCADA model was there. Now we used to be, once the digital twin come in picture, what we did is we try to make a 3D model of that particular plant, including the pipelines, which are connecting 2, 3, 4 plants together. Like one plant is in Mathura, one plant is in Panipat, one plant is in Bhatinda, and another plant is in Bangalore. So we are connecting all the plants together with a 3D model, and we simulate that model together through the SCADA and other modeling AI models and other things, and that's called the digital twin. And once the data is live, we can take the decisions. So on the basis of AI, on the basis of that, but this particular part is going to be, it needs to be changed. That decision we can get on the basis of the data. So there are 5 blocks, particularly, which I already being described as of now, but it is just being focused for that physical asset, which was real asset, which we have around 60, 70, 100 years before. Industries are long back, actually. So that's called the physical asset. Another call is, once we wanted something good from the physical asset and we wanted to be scale the health of the physical asset, we need to put the sensor. It is just like you are giving a vaccine to the baby. So he will be healthy. So that's the same thing with the plant, that yes, we are going to give put the sensors at each and every critical point so that we can get the data for that particular point. Now the data platform collects and clean the data. What is the cleaning actually? The cleaning is you will got, if there is a pipeline and you have a fiber optics on that. Fiber optics is a works like a sensor. If something is stamping on the pipeline, on the from the not directly on the pipeline, even on the earth where the pipeline is going underground, what will happen is that particular stamping signature you will get in SCADA system, but you doesn't want it. That is a actually a false alarm. So you remove the false alarm by cleaning the data. So this is where the AI help you. Now there is an action on the dashboard is already being, and now the LLM models and other things are there, but before it was not there. So the people was taking decision by their own brain. Now the AI is taking their brain, and the AI is taking the decision that a particular point is pretty critical. Now go and treat it as soon as possible. If the plant is 80 years old and another plant is 10 years old, which plant needed most attention in terms of the maintenance? Can you please let me know?
So the older one needs.
It is just like a human body.
Yeah.
If the people are 50 years old, they need to be check an yearly checkup every time. So the aging of the steel is one of the pointed thing that if there is an aging of any asset, what you need to do, you need to be taking care of that more cautiously. If the plant is new, yes, the plant can run on their own speed, and yes, we can give some vaccines to that particular plant just like a baby. So it is how we are taking care of chemical plants. We are taking care of other assets, not only chemical plant. Even the every asset is being taken care uh, by this method. And yes, AI and digital twin is helping us a lot in this. But the problem is with the old plant, because putting the sensors there are pretty critical. But the initial SCADA sensors and other things are working there. But now the things is being changed. Everything you can see on your laptop. Hey, where is the problem is? So this is what I just initially I describe you that crude tanks. Once we take the crude, I wanted to ask one more thing here. Are you aware about the gas is coming to your home? This gas is coming from. Can you understand it? Where this gas is coming from? You are paying to IGL if you are living in Delhi. IGL, where the IGL purchase this gas? In Delhi?
Gujarat.
Gujarat, the gas is producing, the Gujarat is producing gas or not?
ONGC, sir?
ONGC is not producing gas at all. ONGC is just extracting crude from
Extract
Mumbai.
the material, crude oil.
Yes. Yes.
In Hazira, its production is
Hazira is a port actually. So the people are taking this gas from Qatar, this gas from Turkmenistan, this gas from Saudi Arabia, and you would be happy that hey, today food is being cooked by the Saudi Arabian gas. So we do not produce the gas actually. India doesn't have gas. Uh, we only produce our 1 or 2% or 3% of the requirement. The 97% of the gas is coming from different countries via these ships or pipelines or something else. And we are also giving our petrol, diesel, and other things to Nepal and Bangladesh. Bangladesh, we have one friendship pipeline. You can search on Google, and just now we put one pipeline to Nepal as well. Just now means 2-3 years before IOCL did this. So we are dependent on gas to other countries. Even for crude oil, we are dependent on Russia. That's why every war is there, everything is there. So you need to understand the global scenario in this regard. But our focus is to be health of the structure, health of the asset. So I will come there again. And the crude oil, once we have the crude in tanks, even the crude in ships, we try to pull out that particular crude from ships to our refinery. This crude comes in different, uh, I can say that the different quality, and so the distillator is required to be there. Okay, this distillator need this type of quality. Once uh, uh, the things is being divided into multiple part, not only 3 part. These 3 part is just for your sake of, otherwise there are around 20 to 24 parts sometimes. So we distribute this crude oil into the naphtha, diesel, petrol, residue, multiple things, and these things will go to the client side through pipeline, otherwise through tankers or whatever the required mean is. With the digital twin, you can see that how much oil we need to supply to Delhi, how much gas we need to supply to Delhi, how much energy, how much tankers we need to be there at Delhi plant to be supply our cylinders to home. So everything should be on live, because you need to aware about how many gas is how much gas is being consumed in a day in Delhi, so that you can purchase the required gas from other countries. So it is just a live mirror. The digital twin is a live mirror of the of the things to it will help to take the decision that how much gas and oil you want it to be purchased. It is just like an oil at kitchen, yeah. So in monthly that you are consuming 1 liter or 2 liter of oil in your kitchen. It is not the petrol. It is an different type of refined oil and sarso tail and other things. So you cannot do like, hey, I need the 200 kg oil today, yeah, 200 liter oil today at home, and I will consume it in 3 years. So it is not like that. So taking that decision as far as the country concerned, you need the live consumption and everything to be in live, and the digital twin help in this. Once you have once you push the petrol from Mathura to Delhi, how you will push it? Can anyone have an idea that if the crude oil or petrol or something is coming from Mathura to Delhi, even the gas is coming from Gujarat to Delhi, how this gas is coming from Gujarat to Delhi? Anyone of you? The pipeline is there.
My pipeline is
The pipeline is there, but how it is being pushed off? If I am putting a gas in the pipeline in Gujarat, and the gas is coming to Delhi, how the gas is flowing? The gas doesn't have their own mind.
so
Sir,
are we applying pressure?
pressure gradient of sorts?
Gradient Gujarat is lower than us. That's why the sea is there. We are on upgrade. So the
So
gas
they are
should go.
pumping station every 100 kilometers.
Yes. So they have not only every 100 kilometer, it depends that how much pumping is required. But you are very right. You are very right. So they are having pumping station that create a pressure difference. Once we are putting the things in Gujarat, there will be a high pressure, and that pressure will be low till this come to Delhi. If the pressure is pretty very low, then what we do, we put a compressor station there, so that that particular pumping station will push the gas again. So this everything is required to be that you need to monitor the pressure each and every point of particular point of time. uh, I'll say you that this is one of the pig launcher and receiver, the pumping station in between. If there is two new, this you can consider this pipeline as a 200-kilometer pipeline, and if there is a new three industrial area is being come on that particular pipeline, that particular pipeline has started feeding those three industrial area, then the pumping station required more. Then more pumping is required to push more gas to Delhi. Otherwise, the gas will not come to Delhi. It will consumed by the people who are having uh, the industrial area on this particular pipeline. So that pipeline is a bloodline actually for the country. That's why I'm saying again and again, this pipeline is a bloodline for the country, and we need to monitor these pipelines, and we are monitoring these pipelines through digital twin. Digital twin required more data. If more and more data will strengthen the digital twin decision making power. Uh, um, as the VDT concerned, this is my company. We are into ILI, oil and gas ILI inspection. What is ILI? If the pipeline is 300 kilometer, you cannot dig out the pipeline and inspect that particular pipeline each and every point. So what you need to do, even you cannot close this pipeline, you cannot shut down this pipeline. Hey, we are stopping this pipeline for next 6 hours. That
So you are disconnected.
Hello. I think there is some
Internet issue
internet
at sir said.
Disconnect हो गया channel.
Sir will join shortly.
ना mute जाए.
Are you able to hear it now?
Yes, sir.
I'm again come to disturb you. So
You are audible.
You are
Let
audible,
me
sir.
see, sir, whether you are the co-host right now or not.
are you
Yes.
able to see my video,
Yes, sir.
right? And
So you can
actually,
continue.
okay, perfectly all right. So you are able to see my screen as of now. So again, actually, this was on
No,
track.
no, sir. We are not.
So kindly reshare it, sir. It's not visible.
Okay, once again.
Yes, sir. Now we can see.
I request everyone to be stop your videos. Otherwise, my connection is on phone, so it can disconnect again.
Fine, sir.
So, perfectly all right. So, can I start right now? Okay.
Yes, sir.
Okay. Thank you. So inline inspection is the ones we are putting our robot inside the pipeline. Inside the pipeline is not an empty pipeline. It is the pipeline where we put our robot filled with LPG, filled with the petrol, filled with diesel, and we are putting lithium batteries there on a very high pressure and high temperature sometime. So this kind of risk and this kind of uh, uh, advanced engineering we do with the advanced engineering robots we put inside the pipeline and inspect those pipelines. I think 300-kilometer pipeline we can inspect in 36 hours. This is the fastest NDT method of the world. NDT is non-destructive testing of the world. So now come to again that this is where this digital twin come in picture. The data coming from the multiple sensors in edge computing. By taking the decision, now this edge computing is also advanced. They are by having the AI platform to reduce the false alarms, and then we put these all data to our cloud platform, or somehow this cloud platform or local as well, and we take the decision on the basis of uh, digital twin on the some historical twin that yes, it happens in this particular pipeline, and once our sensor was giving this value, so that system start learning by themselves. There are things is in AI. You are better, you know better than me in this. The hybrid twin, is best in both. This is best, the physical models and the machine learning models. But the system is being grown better than this nowadays. Once you come to the predictive maintenance, how the system is taking decision. The system is taking decision on the alert threshold. The things are started like 10%, 20%, 30% of the corrosion in that particular asset in any chemical plant. This is not an high alert. If the pipe plant is crossing their threshold limit can be 80%, 70%, or 60%. It depends on the how much pressure is it is being running in the pipeline. Then you can take decision on that particular threshold, or on the basis of that particular threshold. We do repeat ILI run again and again, and that data we supply to that digital twin. Yeah, take the decision now. This is the condition of your pipeline. There are other things as well, like leak detection. So I told you that we put fiber optic sensor on all over the pipeline, 300 kilometer, 1000 kilometer, 2000 kilometer. Even currently in India, there is 1 lakh kilometer of the pipeline network. So once you need to be that is there 1 lakh kilometer is not going to be leakage. It is not. It is not going to be happen. So we put sensors and take the decision on the basis of the sensors value. The optimization, this also increase our efficiency once you are into the energy optimization. As I told you that if you require 2 liter of oil in your kitchen, it is not right to put 2000 liter of oil in your home at one time. So this is the energy efficiency, means that at the home we are budget efficiency we are using, and at the same in the plants we are using the energy efficiency, how much oil is required and which type of oil is required. That the digital twin is also capable to give us uh, give us the data on that particular point as well. What is next? Everyone is saying that hydrogen is coming. Hydrogen is coming. Are you aware about the what is hydrogen energy? Even the carbon pipelines, even the methane pipelines. Methane is not there in the slide, but methane pipeline, green gases pipeline. Autonomous robot will drive this digital twin. Even after some time, there will be no person is required in any plant. Currently, in each and every plant, there are lot of persons goes inside, like 1000, 2000, or 3000. After some time, nobody is required inside. Hey, please go, please leave out, please be stand outside. One person will take care of all over the plants. This is with the help of digital twin. It is not like the job is going anywhere. The job will not go anywhere. So there are other things will come up. So hydrogen ready pipeline network and hydrogen ready conversion network for every country all over the world is needed. Once the hydrogen will be there, these integrity assessment have more responsibility. Even the digital twin has more responsibility. If hydrogen will leakage, you cannot even assess the what type of damage can be done. Digital twin gives a picture. Actually, this gives a real picture to you that, hey, this is going to be happen. Not 100% real, but it gives the 90%. The people are taking decision on above of that, but the 90% is decision are uh, uh, being taken by digital twin data. But digital twin doesn't know that how much money today I have in my pocket. So we need to put these things once the digital twin give their feedback from the plants. If you want it to be the twin engineer, the digital twin one, the Python is the base. You need to be. It is just like an Hindi and English. You need to aware about the IoT sensors. You need to aware about how the plant is processing themselves. And what is the NDT inspection? NDT is non-destructive testing. There are few methods are available for NDT in the world, and one of the method we have developed in India. And thereafter, you will be able to give your data to twin or digital twin or a SCADA system, and then the digital twin can take a decision on that on the basis of particular data. Thank you so much, everyone, and thank you to be in my lecture for patiently. Thank you. Anyone have any questions? I'm ready to answer.
Thank you, sir. There are few questions. One question is that what is the biggest challenge in implementing digital twins for the India gas pipeline network?
Indian gas pipeline network, the actually pretty old pipeline network. Once we were 60 years old, this pipeline is being laid 80 years or 60 years before. Once there was no sensor. Now you wanted to put sensor, you need to dig it. because if you will not dig it, you will not be able to put sensors there. So this is one of the biggest challenge, that you cannot open thousands of the kilometer of the pipeline which is buried as of now, and again put sensors on that. So that's why what the current scenario is, once you are establishing pipeline, once you are establishing you are putting one pipeline of 1,000 kilometer or 2,000 kilometer, this digital twin sensors needs to be there at point of time, and it should work right. So this is the biggest challenge. Actually, the old pipelines are biggest challenge.
Okay, okay. Thank you, sir. One more question is that, can digital twins be applied to other infrastructure such as water supply, power grids, or smart cities?
Yes, yes, yes. This is actually for the major asset. It is already being there. In developed country, it is already being there. Even the water supply, the government wants to supply the water from one place to another place. It is 1,000 kilometer away from here. But the thing is, if you are not supplying this particular, uh, uh, if there is any leakage in between, the water will not go that particular point where it is needed. So digital twin is there. If there is any leakage, who will tell us that, hey, leakage is there, you need to be uh, uh, open the pipeline and treat it as soon as possible. So in major asset we have, but in smaller asset, which is the pipeline is coming to your home, we do not have it.
Okay, sir. One more question is that, if a pipeline runs through a remote or forest area without internet, how SCADA sensor can transmit real-time data back to the headquarters?
Internet is required. Internet is just internet cannot work underground pipeline. So what you need to do, this is other method to get the data, like optical fiber, like lidar, and other. There are a lot of method available. Everything is not depend on internet.
Yes, sir. Yes, sir.
In space there is no internet. How you do this? The in even in underground, like sea, the deep depth of the sea, there is no internet available. In tunnels, there is no internet available. So the communication is there. So you need to establish the communication protocol. That's it.
One more question is that,
Let me
sir, 1 minute.
How can AI improve digital twins?
Sir, how can AI improve digital twin prediction beyond physics-based models?
The AI is a kind of the AI started basically from physics and math. Now they are able to, this model is able to take the decision by their own themselves. AI we are using from last so many years, right? So there was telepathy, that was also an AI. So if you relate it from your past, even the Rishi Muni time, then AI was also there. So the things is, AI currently, if you are talking about LLM models, yes, the things are improving day by day. But it is always like, to taking a accurate decision, you need an human help. Once you need an human help, you put that data to the AI learn through the human experience and start taking decision on their own basis, on their basis. And sometimes the emotional and other uh, the things are required to be take decision, then the people are thinking that, hey, I need to look at what the decision is right, giving by this LLM model or not. But nowadays the AI comes to the emotional and other things as well, so it is grabbing your mind, that, hey, you need to take decision, I will take a decision on your behalf. You need to marry this girl or not, I need to take this decision on your behalf. So this is the AI is currently doing. Yes.
More question is that, how does the robot detect the change in pipeline? Do they check from surface to surface? And what is the SCADA system?
I
Can you
think
please
sir has
come,
explained.
madam, can you please come again for this question?
So how does the robots detect the change in the pipeline? Do they check from the surface, and what is the SCADA system? I think you have explained this in detail.
I'll tell within very our robot is going inside the line, not on the surface of the line. If you want to check the pipeline from surface, this will create another quest. You need to open the 3,000 kilometer of the pipeline and then check and then again bury that particular pipeline. So it is not, it cannot happen. So this is number one answer of your question. Another answer is SCADA system. SCADA system is the one place where you are getting information of all the sensors, all the plants, how much the petrol, diesel, and crude you have being supplied to the furnace, and how much is being coming out. This everything is depend on SCADA system. SCADA is a ascent group of digital twin that you can think of.
Thank you, sir, for such a nice session. I think all the participants are satisfied with the answers. Now, your presentation has provided us with a clear understanding of how digital twin technology is transforming the chemical industries through the real-time monitoring, predictive maintenance, process optimization, and improved operational safety. Your expertise and practical insights have inspired all of us to appreciate the growing role of the digitalization and industries in chemical engineering and process industries. Thank you very much, sir. Now, I want to request to all that please switch on your camera so that then we can click a group photograph. Thank you very much, sir. Thank you
Thank
once
you,
again.
madam. Thank you so much.
Thank you, Kirti. Now it is the time for our third technical session. And the topic of the session is smart factories in petrochemicals, polymers, and specialty chemicals, industrial IoT, and AI integration. For this, we have Dr. Vishal Singh with us. And now I would like to call Mr. Mahadev Swami to introduce our distinguished speaker and conduct the session.
Thank you, Ashima. It is my great pleasure and privilege to welcome our speaker, Professor Vishal Singh, Department of Design and Manufacturing at the Indian Institute of Science, Bangalore. Professor Vishal Singh holds a PhD from University of Sydney, a Master of Design from the Indian Institute of Science, Bangalore, and a Bachelor of Architecture from Birla Institute of Technology. With a extensive academic research, international experience, he has established himself as a leading researcher in the field of designs, innovation, and intelligent system. His research lies at the intersection of artificial intelligence, design thinking, computational thinking, system thinking, and Industry 4.0. His interdisciplinary works focus on developing innovative solutions for complex challenges in smart manufacturing, product designs, construction, informatics, digital transformation, and innovation ecosystem. We are truly honored to have a such expert with us today. We are confident that his talk will provide valuable insight into a transformative role of AI and intelligent design in shaping the future of Industry 4.0 and smart manufacturing. Without further delay, it is my honor to invite Professor Vishal Singh to deliver his keynote address. Sir, the virtual stage is yours. Over to you. Thank you, sir.
Thank you. Am I audible?
Yes, sir, you are audible.
Thank you very much. Thanks for that detailed introduction. Let me put up my slides and I'll get started with that. Just give me a moment.
Okay, sir.
Please let me know if my slides are visible.
Yes, sir, it is visible.
Yeah, thank you very much. So there's a slight change in the topic. I thought, given my background in design and digital manufacturing, smart factories, I thought I'll focus more on these questions, and even my connection to AI will be very fundamental. So I'll not go too much into detailed applications, though I'll give some examples of what we are doing. But it's largely very basic, very theoretical, hopefully with the idea to, because I was hearing the questions in the last talk towards the end of it, and questions around AI and so on. And given my experience also with students at our institute as well, I think it's always useful to understand the historical context. Though I'm not going into the history of AI, I'll touch upon a bit of background into what is generative AI these days, or even before generative AI, there was something called generative design. So I'll start with that perspective, and hopefully that will give you, the audience, some sort of connect to where things are heading. So as I said, I'll focus on smart factories, digital manufacturing, not so much on industrial IoT as such, though I'll touch upon some of the background related to that. Though you have already sort of given the background, I just wanted to make it explicit where I come from. So I have three broad areas of research. One is in the space of products. These products need not be products at small scale, but products like buildings. So how do you consider buildings as products? Factories, how do you build factories and things like that? So that's where the smart factories research comes. There are three broad areas of research that my group does within this. One is product lifecycle management. The other is smart manufacturing and the role of Industry 4.0. And in many of these, again, coming with our strong design background at the institute, we are looking at also prefabrication and modularity, even at the level of factories. And also, how do you build factories faster? How do you make them modular? How do you build plug and play factories and things like that? So that's the one area of research. The second area of research we do is how do you solve problems? How do you implement computational systems? So this is where design thinking, systems thinking, and computational thinking come. The whole objective of all of this is to help people make better decisions. I think that was the last point being made earlier as well, that AI is largely to help make better decisions. Whether you automate that decision or whether you support humans making better decisions, eventually all of the computational effort is to make better decisions. And in doing so, we also develop a lot of tools and methods that help you make better decisions in design terms. So right at the beginning, let's say you design your factory, you design your product, you design your organization. All of these are to be designed. So how do you develop tools and methods to support that? And of course, in all of this, systems level complexity comes in when you create new things, create new innovation. Then how do you take the innovation to the market? How do you make adoption happen and change happen? So there are a number of questions at systems level. So that's where the third area of research looks at is innovation ecosystem. So you might develop a new product, but nobody wants to use it. So why not, right? So we try to understand it and develop tools and methods and frameworks to support that. So that's the larger background from where I come. And hence, again, a disclaimer that I'm not an expert in petrochemical or polymer. I have absolutely no background there. But as design researchers, we are domain independent, and we, if a problem comes, we address that through our decision-making capabilities and through AI-based tools and so on. And hence, the context is relevant to us. Again, just to give you a quick background, if there are people who have not heard of systems thinking and computational thinking, again, this is not a lecture on these topics, so I'm not going to go in details. But just enough context so that the discussions going forward would make sense to you. So when we talk about systems thinking, we talk about things that are interconnected to each other, right? So typically engineering education or education in India and globally to that, for that matter, has been reductionist, right? You break down topics and subtopics into specializations. So somebody studies mechanical engineering and then looks at the world as the world outside, and only the knowledge is about mechanical engineering. Somebody looks at chemical engineering, that's their work domain, and then everything outside their work domain is not their problem. Whereas in systems thinking, you look at the big picture. You look at interconnected systems, and you know that even if I solve my part of the system, it may not work in the overall system because there are interdependencies. So if you are trying to solve problems within a, let's say, an industry or a company or even your own business, It's not enough to just solve one part of the problem, because even if you solve that part of the problem, if other parts are not interdependent, relationships are not understood, things will fail. And that's one of the reasons why we hear so much of blame game, where we hear that I did my bit, but the others did not support it and so on, right? That's largely because this systems thinking is missing and the holistic view or the whole picture is not seen. Systems thinking talks about that as a critical call. So that's one of the key points. There are several aspects of systems thinking. Once you start by realizing that everything is connected to a larger system, and hence if you want to make a change in whatever part you are solving, you have to understand its dependencies with the other part of the system, right? That change in perspective can lead to a number of things. I'm not going to go there, but one of the challenges it brings in is that things become very complex, because one of the reasons why I decompose them into one part is because it's easier to solve one part and reduce complexity. So the whole question then from systems thinking perspective is about managing complexity. At some point, you have to decompose the problem and solve it. But at the same time, you have to look at what you are solving is connected to the larger picture, what is the interface. That is where modular thinking sometimes becomes useful, because even if you are solving your part, you know how it interfaces with the other parts. And if you are aware of the dependencies and the interfaces, you'll be able to solve your problem while knowing how it connects to the rest of it, right? And so that's the larger picture. Again, I'm not going to go into it, but hopefully the examples that I'll give you will give you some connect to systems thinking. I also, in the process, will introduce a number of concepts. So do not worry about the specific concepts. They are not important. What is important is the way to approach them. And if you can see an underlying pattern, and I'll again connect back all of that to all the current discussions about AI and generative design, generative AI, and so on. So from that perspective, if we look at, as I said, a good amount of my work also happens in construction. So this is a slide from how we look at digital twin within construction and its use. And so one of the questions earlier was asked about where all can digital twin be used. Digital twin can be used everywhere, as was answered by our previous speaker. So this is again in the context of any system, if you take for that matter. Industrial system, construction as an organization, petrochemical. There are essentially four aspects of a system, if you take it from a system of systems perspective, right? All organizations are a social system. When I say social system, which means that there is an organization. And if there is a project, maybe there are multiple companies or multiple organizations working in them. Each organization is organized into teams, project teams, and within project teams, you have sub-teams and so on. And within teams, you have people, right? So a number of challenges in any project also arises purely within the social system itself. So this is what is referred to here as human social systems or human systems, right? This is where a number of people within social sciences work, but this should something that also affects engineers and designers and anybody who's trying to solve technical problems. You cannot ignore the reality that you work in a team or an organization, and you have to follow the protocols that are there in the organization. Now, all teams also have a number of software systems to support them, right? So this is where your CAD systems come, your PLM systems. You talked about SCADA and all of that. All kinds of information systems allow you to connect different teams. Now, anybody here who's done some research on information systems would have heard of the term called interoperability, right? When you have multiple different software, multiple different systems working in an organization, even within these softwares and tools, it's very difficult to communicate from one tool to the other. If somebody does programming, for instance, you might sort of learn one programming language, and then you cannot directly translate that into another programming language, right? So you see that the interoperability is a very big question. That's not just true for information systems, that's true even in languages. So let's say somebody knows only one or two languages, goes to a new state or a new country and does not understand the local language. That's again a question of interoperability, right? So interoperability in any system becomes another critical aspect, which is also true of software information systems. In any organization, so you have people, you have software information systems. This includes your WhatsApps and direct messages and all of that. The third kind of system that you have is typically these hardware-based technical systems, where we talk about more sensing sensors, sensors including optical sensors like cameras, other kinds of sensors, transducers, and things like that, which allow you to communicate, right? Including, for example, an alarm. So, for example, let's say if something happens, an alarm buzzes loud, who's that alarm for? So that alarm typically is to communicate to humans, human users or human system that something has happened, right? So these are communication, direct communication between your hardware technical systems and your human systems. And in most companies, besides all these three things, if you work on a shop floor or if you work in a site, you'll realize that there are a lot of things still on signboards and notice boards and things like that. So this is what we are calling as analog systems. Now, from a system of systems perspective, if you want to make an effective organization in any industrial context, whether it's a smart factory or outside or in a oil field or otherwise, you need these 4 types of systems to communicate to each other, right? So people should be able to have access to the software information systems. Software information systems should connect to hardware information systems and all of that, right? So this is the perspective with which we develop digital twin. So digital twin is not developed only of the product, but you can also develop digital twin of the software systems. Or now the question is, what will be a digital twin of a software system? So that's something I would want you to think through. And maybe if you have doubts, you can ask me questions towards the end. Similarly, what would a digital twin of a social system look like? If you have a team, what is its digital twin? These are ideas worth thinking about, because as eventually what we are trying to do in all of these is to try to understand, can we track these systems, right? The whole purpose of a digital twin is that you are able to have bi-directional connect between the system that you are cloning and the representation of that system in some other place. If that is true, then you need to have means and ways to monitor, track that existing system, and of course, give a feedback and communicate and bi-directionally change the system or alter the system or give an input to the system if you want to, right? I'll leave again the theoretical bit here. As I said, there'll be a number of theoretical concepts introduced. So feel free to ask me questions, and I'll keep my presentation short so that I can take more questions towards the end. Now, here's an example of, this is not a situational awareness platform. Okay, so before I move to that, let me clarify what we mean by. So here is a term that you see on the top, which is called situational awareness. In my group, one of the research we do is in the area of situational awareness, which goes beyond the idea of digital twin. So digital twin essentially talks about having a replica or a clone of some other system so that you can see what is going on. Situational awareness, on the other hand, talks about a research where we say, how do we get the right information to the right person or the right actor? It doesn't have to be the person, it can be an artificial agent. How do we get the right information to the right actor at the right time so that they can make the right decision? Now, for them to make the right decision, the information should be actionable. That is, you give the information in a way, in a format, and presented in a way so that they can actually make sense of the decision and act within reasonable amount of time. This is different from digital twin, because digital twin just gives you an update of what is going on, but it may not necessarily give you an actionable information. Again, it's a subtle detail, but there's a lot more to it. I'll be happy to answer again more details on that. But the idea of situational awareness is, let me give you an example on that. So all of us know what is going around in the world in terms of the politics, geopolitics, and so on. How do you get that information? So you go and watch a 10-minute news. You know that, okay, the oil prices are going to go high. There's a war in Iran or something else. And now that's an actionable information that helps you make a decision whether to buy your LPG cylinder or otherwise, right? So you are able to take an action because you're part of a larger global system where something is happening somewhere in the world, but it's going to affect you. And hence you must take an action. That is your situational awareness. Similarly, let's say if you have in your office or at your home, you have somebody going to, let's say domestic help is supposed to come and help you, but is not well and may not come today. So you know that, okay, you might have to do the work because somebody is not going to come today, right? All of that is part of your situational awareness so that you know that given the change in situation, I have to react and I have to do something, right? This is a very common problem in all organizations, whether you are in a petrochemical industry or any other industry. So our overarching research question here is, how do we create situational awareness within an organization so that the right actors can respond to the problem as and when it is required? And many of these problems come unplanned and they are uncertain. And hence, just technical information systems may not be enough. You have to develop processes around it to enable that. And that's the research question we are addressing in our research group. Now, this is not, as of now, this is not a situational awareness platform. This is a
Sir, your voice is not audible, sir. All participants kindly wait for 2 minutes.
all right, just give me a moment. Sorry, I had a power cut and I had very little situational awareness of that. So give me a moment and I'll put on my slides back again.
Okay, sir. It's okay, sir. No issue.
Right, can you see my slides?
Yes, sir. It's visible.
Yeah, thank you. So as I was saying, I mean, and there itself, you saw the example right there that things can happen unplanned and sometimes you are not able to track or expect that, right? So how do you sort of design for systems, digital twin for that, and how do you enable quick response to those situations? I'll quickly play this video. Just let me know if the video is playing properly.
Yes, sir.
Okay. So this is a video, this is specific to construction, but largely it's a facilities management platform. And I'll explain what's happening in the platform once you see the the basic video. So this was the work of one of my PhD students. This was done in Finland when I was there. And I'll explain the context within which it was developed and is as applicable to smart factory as it is to any other types of buildings. So I'll let the video play and then I'll explain it. Okay, I'll pause it here. The whole video need not be played, so let me just sort of explain. Yeah, so what's happening in this video, as you see, is there's a building with sensors of different types, including, so on the right side, what you see is essentially the specific rooms or locations where the facility manager is interested to check what is the room temperature, air quality, and all of that. On the video itself, in between, you had seen there was this green patch. And in this green patch, what you see here is the sensor data. All your sensor data and everything is coming here. And this is live monitoring of the building status. Now, what we found is that while this system was developed for the facility manager, the end users may equally be, let's say you are working in a specific zone in your factory, and you are interested in knowing where to or communicating about change in room temperature and all of that. You can change. So here you can see that there are 3 different views. So you have a view where somebody can check a specific object. For example, if I click on this window, it shows me in which part of the building is this window located, what are the details of the window, who's the guy who maintains the window, and so on. So that way I have an entire building's detail at all scales. So if I want to get to know who actually maintains it, who will come and fix it, what are its attributes, if I have to order a new window to replace it, who is the manufacturer, all those details can be obtained from this platform. So what we have developed is a data aggregation platform which collects all this data. And from here as well, if the facility manager wants to control the temperature in a room, they can actually go to the sensor. And so all of that is connected here, but they are not directly controlled from here. So the communication from this platform goes to the team that manages the sensors, and they can decide whether to allow that temperature to be raised or not if they want to change the room temperature. So that's where the actuator is, right? So essentially saying that technologically, this is possible. And this was done in 2016. So this is, I'm showing you a platform that was developed 9 years ago, right? This platform aggregates data from the building. So basically all the building data, aggregates data from the sensors, aggregate data from the environment, aggregates data from people, because people can feed what they want to communicate, and so on, right? So it aggregates data from multiple sources. Now, I've briefly talked about systems thinking, and I said systems thinking is about connecting and understanding interdependencies. And then I showed you a computational system, right? Where we said, okay, you can develop a digital platform to connect different data sets. Eventually, we are interested also in, as the topic suggests, that we are also interested in AI. Now, AI, if we talk about AI, we are already talking about computational space. How do we compute? And as the previous speaker also said, AI is an extension in some sense of our long-term desire to make better decisions. And hence we develop all these systems to improve decision-making. Now, decision-making in that sense is nothing but computation, right? When you and I also take decision, we also compute. We take information, we take data, we process data, and then we decide what to do. All of that computation goes on in your mind. So computational thinking as a field, again, is not something that's taught very regularly in Indian schools. But in many other places, especially in the US and all, they started around 2005 plus. They started teaching computational thinking in schools. And many of these AI leaders, they constantly and regularly talk about the need to bring computational thinking to teaching in schools as well. So if you think of computational thinking as a basic ability of humans, or any system for that matter, to compute, there are 4 aspects of computational thinking. First is, as we discussed right at the beginning, that if the problem is complex, decompose it, make it simpler by breaking it into parts, and then solve each of those parts and at the interfaces and so on, and then connect it back. If you go back to your school days, the way we used to solve maths problems as well, we used to do the same, right? Or for that matter, if you have an engineering team which designs, let's say, an automobile, they decompose the automobile into different teams. So you have a team working on chassis, you have a team working on brakes, you have a team working on the powertrain, and so on. And each of the team then solves for their problem, constantly talking to each other so that they know the interfaces and they solve it, right? So ability to decompose the problem into meaningful ways, which can be recomposed meaningfully, is a very important aspect of computational thinking. The second aspect of computational thinking is the ability to see patterns, right? That's why most of the AI tools or most of the machine learning tools focus on pattern recognition. So you give it a lot of data, and from that data, it tries to learn patterns. Humans also do the same. When humans do the same, we often call it stereotyping, right? So every year you see that, people from a certain continent win the Olympics, 100 meters, and then you assume that the next guy in the line who's from that continent is likely to win the 100 meters. Because we have seen that pattern, and of course, we have our bias from that pattern because that's all we have seen. And hence, the pattern that you see leads you to stereotyping. So while the ability to see pattern is a great capability, stereotyping comes from the bias, but that is also true in machine learning. In machine learning also, you must be aware of the bias in your system. The third kind of computational thinking is algorithms. Algorithms are essentially where you decide or figure out the sequence of steps which help you solve the problem. And that is what you do writing algorithms. And the final aspect, which is very important in computational thinking, is the ability to abstract and represent the problem. So here I'll give you an example again. So if I talk about, let's say, two sides of a coin, right? So two sides of a coin, when we say, we abstract saying that the coin has two sides. But in practice, a coin has three sides, right? But why don't we talk of the third side normally? Is because the third side is, in most problem contexts, not important. It's only occasionally it becomes important. For example, if I am designing a coin sorter, in which the width of the coin becomes important, the coin sorter, then the three sides of the coin become important, right? So similarly, if you are solving, even if you are building a digital twin of a system, you must know what is it that I'm building a digital twin of. Do you build digital twin of every detail of a system or the details that are important, right? Even in a petrochemical industry, that the same questions will arise. And hence, if you want to structure your thoughts in how to think about AI, how to think about digital twin or any of these computational systems, I would encourage you to think about these four aspects of your problem to begin with. And based on this, I would now give you some examples which demonstrate how computational thinking can be applied. So I've taken 4 techniques. Don't worry about the techniques specifically. And each of these techniques can be applied to different problems within the space of generative design or generative AI. So nowadays, you probably ask ChatGPT or Gemini to give you some design, and it gives you a design. Right now, ChatGPT or Gemini is giving you a design based on statistical patterns. Statistical patterns are fine, but they are not causally well thought through, right? Statistically, it makes sense because it has large amounts of data. But the reason some of these systems still fail even in simpler design problems or simpler problems is because they do not causally reason. This is where thinking from additional methods which have been used traditionally in generative design could be useful. Again, you don't need to know these methods. As I said, I'm just going to show you examples. This is only to get you interested in thinking more fundamentally. So here's an example of agent-based model. So here what you see on the left side is an example where 2 students in a 2-week class in one of my courses implemented a system where they implemented a system to decide how to lay out the footpath in a landscape such that people do not walk in between the grass, right? So what they did was they took the statistical data of how many people work in which of the buildings and how many exits and doors are there in these buildings, and from which building to which building they typically go at what time of the day. Based on that, they created a agent-based model, which in an agent-based model here, once a person comes out of a room, other people follow that person. If let's say if you're going out for a lunch, if you are walking on a unplanned path, the others are likely to follow you on the same path. It's like the ant behavior. It's called swarm intelligence. If you do that for a number of people and a number of days, you get a heat map. That heat map can give you this green kind of a pattern, and that will give you the layout that's desirable such that people walk on that footpath. Now, agent-based here, what you are doing is that you are giving each person is represented as an artificial agent in your simulated environment, and they make their own decisions on where to go. And based on that, you are able to simulate the behavior of how people move in a campus, for example. Similarly, you can model that how people would work in a factory. So, or how your AGVs in a factory will move around. So I'll show you an example of one of the factories. This is from YouTube, so you can look at the details later. This also uses agent-based model. In fact, this video that I'm going to show uses the same agent-based model that air traffic control uses to manage the flow of traffic in air, basically planes moving from one place to the other. Is the sound playing from the video?
No, sir.
Okay, just give me 1 minute. Let me check, and maybe I'll have to share computer. Okay. Yeah, just let me know if the video sound plays.
Sure, sure.
Was it playing now?
Yes, sir. Audible.
Okay. Okay, in the interest of time, I'll stop the video here. But I'm sure many of you would have seen these kind of videos also from Amazon warehouse and many other warehouses, which are increasingly becoming more and more fully automated, right? These are smart factories where things are moving from one place to the other, all autonomous systems. How do these systems move? How are these multi-agent systems managed through AI and your technical systems? They're largely based on agent-based models of this nature, right? Where each of these entities is given its own agency. They make their own decisions. They talk to each other, which means they communicate to each other, and then they are able to sort of work out. They also check, for example, where, let's say, a work is required, they move to that location. There could be a central agent which communicates to these agents and so on, right? Hence, if you are interested in smart factories, AI and related things going forward, or generative AI, it's not enough just to sort of use the tools, but to understand the background work that has gone into the development, the history of these developments, to understand how these tools function. Because once you understand the basics, it becomes a lot easier to implement the systems and leverage them for what you want to do. So let me, in the same spirit, show you a few more examples of different other things, and that will hopefully give you some ideas. So similarly, just like agent-based models, there's another way to decompose the problem. It's called cellular automata. Now, what is cellular automata? Essentially, what it does is it divides a space into grids. It's a matrix. And the grids, each of those cell is given a cell state. And there will be neighboring relationships between cell states. For example, think of a chessboard, right? So in a chessboard, you divide the chessboard into 64 cells. Now you give rules saying, first of all, alternate adjacent cells are black and white. And then you give rules of which piece can move, how many moves on which side and according to which cell, right? Now, even with those 64 cells and only say 32 pieces of, or not even 32, essentially 10 to 12 pieces of different types of chess pieces, you have infinite possible game moves. How is that possible? That is possible because of the nature of complex systems, right? So you have 2 to the power of n possibilities, and that then again further expands if you take the number of types of pieces. So it becomes infinitely large number of moves to think about, right? But essentially what you are able to do is that if you break it down further, the whole game can be represented by just those 2 types of cells, black and white, 2 types of pieces, black and white, and those number of pieces and their number of moves. And if you define, if you understand that, all other possibilities emerge from that. So cellular automata in a similar spirit sort of divides the world that you are trying to solve the problem into grids and says what rules determine the functioning of this world, right? For example, I'll show you an example here. I'll show a couple of examples, and hopefully that will again help you here. So here, some of you might have done CFD if you have a mechanical engineering background. So in CFD, you are trying to model fluid dynamics. This is one example of use of cellular automata-based fluid dynamics. So in this case, what is looked at is that if you look at any water droplet, all the neighboring droplets will be affected by that, right? So there's so this is one kind of neighborhood. This droplet will exert some force on the neighboring with some velocity. And I mean, there will be some velocity and some force and so on, right? So with all of that, I can take any droplet and define how it influences the neighboring droplets, right? Based on just that model, you see that this simulation was done. So this is a lattice-Boltzmann method for fluid simulation. I'll just let it play and then you see. So here in this case, on the path of a fluid movement, we have put 3 cylinders vertically. So basically you are seeing the cross section of the cylinder. And then you see how the placement of these obstacles affects the movement of fluid, right? So what you are seeing is the blue and red is the fluid movement affected by an obstacle placed in front of a moving fluid. We'll see some more examples on this in the same video. Now this is fluid movement within a pipeline, right? So if you are moving things within a constrained space, how does the fluid move along the edges, along the corners, and in the other places, right? And you can see that this starts to model things which are very comparable to the empirical data. What you actually observe in the movement of the fluid can actually be simulated now through a model which simplifies it into this kind of relationships. Right. So in some sense, this becomes your physics-based models. The only thing is the physics here is to be understood in a certain kind of representation, right? Similarly, for example, so it's very important to understand what is a representation. For example, if you think of calculus, that's one kind of representation of a problem. Cellular automata is another kind of representation of a problem, and so on. There are different types of representations. Now, let me move to the next slide. I'll give another example of cellular automata. So this is an example where you can sort of simulate how fire will sort of spread or diffuse if you take a particle board. Everybody understands what a particle board is, right? So which is essentially a board which is made out of fiber, and then the fibers will have density, fibers will have direction, fibers will have length. All are parameters that affect how fire will spread. So I'll play the video, and then you can see that at one point the fire starts, and then you can see its behavior of how it spreads. And it's, again, the simulation mimics something very close to what the empirical data shows. So you see the bottom left, the fire is starting. You see the red zone in the periphery of fire, and the spread of fire in terms of speed and direction and so on. So if you change the direction of the fibers, the density of the fibers, the gap between the fibers and all of that, you'll see that that affects the spread of the growth at the rate of spread of fire. Now, if somebody is designing designing particle boards or fiber boards with the intent to reduce the spread of fire or designing it for greater fire safety, you can do these simulations. You can, from this, learn what is the right size of length of the fiber board that fibers should take, what is the direction, what should be the density, what can you do in between to mitigate it, right? So you can add your strategy to prevent fire from spreading and test whether that strategy works or not. All of those could be simulated. Again, the idea here is that if all of these seem very good candidate for AI-based design, right? Or AI-based approach to testing things, simulating things. But all of those have to have some scientific fundamental or some understanding of how to break down the problem, decompose the problem, Now, in order to understand that a fiber board functions like these, when you conduct empirical studies, you are again looking for patterns. From those patterns, that's the pattern recognition. You are learning what parameters seem to be important, and then we are bringing it back to your simulation model. Those patterns that you have learned help you identify what are the parameters to consider in your model. And that one way to do that is cellular automata, for that matter. Is there any question at this point before I move on?
No, sir. No any questions.
Okay. All right, then I'll move on. A third kind of representation is called grammars. Grammars are very similar to the grammar the way you learn in school, which is English grammar or Hindi grammar. Basically, what it says is that you have elemental entities like words. Each word has its own meaning, and you combine words to have the right grammatical structure. If you combine them properly, it makes a meaningful sentence. You combine the meaningful sentences together, it creates a meaningful paragraph. And all of that creates meaning if you have a book or anything that you are saying. So your article has a meaning because it is structured meaningfully. And that eventually, if you break it down, it breaks down to those same words that it can be used to create some other meaning, right? That's the same idea in shape grammar. Again, if you look at it, it's about pattern recognition. So what you're saying is that if I want to generate, for example, many of the temple architecture and traditional architecture used to follow grammars. So for example, if you look at the temples in South India, they all have a very similar style, right? And those styles can be learned. If you learn the style, you can recreate a temple, another temple which looks very similar and it follows the same style, right? So in what you do in shape grammar, you start with some initial shape, that is your building block, just like your words. You have some production rules, just like your rules of how you use noun, pronoun, and all that, saying what can go with what to add what value. You have some operators, which is Boolean operators like join, subtract, and things like that. And then you have eventual outcomes, terminal shapes. Terminal shapes are like sentences, right? The whole idea of grammars is around this idea. Now, I know that all of this would be new to most of you. And that's the reason I wanted to bring this, because these things are rarely taught in the school system or even in colleges in engineering. But once you get at least introduced to it, I hope it triggers some thought on how to approach computational thinking and not just think of applying an algorithm that is there in some library, but think more basic. So I'll show you one project where we use this grammar sort of an approach to create layout for a paper mill. Paper mills are very large. So let me show what a paper mill is. So paper mills are very large factories, right, in which multiple things happen. These are typically factories which have a layout of, let's say, 2 kilometers by 2 kilometers, large sites. So in these large sites, in many places, typically paper mills are also quite often placed near water bodies. The advantage of that is at water bodies and train stations and things like that. The reason is because you move these large wooden logs from, let's say, forest areas or imported wood and all that logs to your paper mill where it is to be processed, right? So if it is near forest areas, it helps because then you can just use the water body, bring your thing and so on. So now a typical paper mill would have wood yard, it will have a pulping facility. All of these are very large factories in themselves. Then you will have chemical unloading, you have bleaching, you have other utilities, you have stock preparation, chemical recovery, post-treatment, paper finishing, shipping, and all of that. All these are big facilities and buildings in themselves. So if you have to design these, it typically takes a long time. So I'll give you the context and history of this project so that you can see how AI can be leveraged or how computation can be leveraged to simplify things. Now, this was the project I got in 2017, where there was that time I was in Finland as a faculty. And this industry partner came. They used to make paper mills across the globe, right? So they used to make it in Vietnam, China, Indonesia, India, and other places. The paper industry around 1990s, toward the late of 1990s, seemed to be slowing down because people said we are going in a paperless world, digitalization is coming, and all of that. So what the company did not hire new designers for a long time. For 15 years, they did not hire designers. People who are doing the layout for the factory. Now, in order to do layout for the factory, you need to have a lot of knowledge, right? You need to have technical knowledge, you need to have architectural knowledge and all of that. And because they did not hire people and suddenly the industry boomed again. So they realized that typically from the point a customer came to them for layout of a factory, they would require many months before even the initial layout was agreed upon. Because first of all, site conditions will vary. Clients will have their own choices. So even if the team gave 3 options within the first 2 months or 3 months, it would take at least a month to create one option, doing the design in the traditional AutoCAD way or any other way. They'll create 2 to 3 alternatives. Every time a client will ask for a change, they have to go back and make many changes and so on. So they wanted a simple system which can create alternatives within, say, 2 to 3 days, and as many alternatives as possible, testing as many ideas. So in generative design, there's something called optioneering, generative design platform. And this is what we developed. We developed a system which was developed in 3 months, and I'll show you how it works. So this was the actual site. And each of those typical buildings that you see have their own assembly line inside, right? Something gets inserted, a lot of processing happens, then the output of these goes to the next building, something gets done, then it moves to the next building. So you have to design all of these buildings and all of those activities. So you can imagine how much time it will take. So what we did was we created a simple platform. I'll just, not a simple platform, but I'll explain what this, but a computational platform. I'll just play the video. What you'll see in the video is that the buildings that you see there, organized and connected to each other, are randomly placed initially. Each of them has its own processing layout. And when you place them, the algorithm starts to organize them in a meaningful way so that the optimization, layout optimization happens. So you see, I had randomly placed these buildings, and then algorithm is reorganizing with each generation. It is testing, optimizing it, moving to the next generation, further optimizing it. So it uses genetic algorithm here to start to optimize the layout of the factory where the right kind of buildings are next to each other so that the input processing from one building goes to the next building and so on. And then at some point, you see that it gets to become optimal and starts to slow down and stabilizes into a layout. This layout takes into multiple considerations. It takes into consideration, first of all, the assembly sequence, which is the production system. It takes into account the site conditions, which means, is the soil appropriate for taking the load of the building? It also takes into account wind direction, because if you have a factory and if you have neighboring city, you don't want the wind to go towards the neighboring city. You might want to want it to go to the towards the forest area or otherwise, right? This is just an explanation of how the platform works. So if some of you have worked in Grasshopper or a visual programming language, visual programming platform, this is a visual program. So this entire design is not done by human designer. The team developed a computational tool, and the tool is generating the design and the design alternatives. And with each generation, it's improving the design by optimizing. How did we model it? Now, this is where the grammar comes in. We said, if you look at any assembly line has a workstation, and whatever work gets done in this assembly line moves to the next workstation. And this is connected by that line. That is the assembly line, right? So if you think of any factory, any one shed for that matter in a factory, there's an input. Your raw material or resources come from one side. At each point, there are workstations. On either side of the workstations, you have some space, either inventory space or an office. For example, there could be an office here to oversee what is going on in this building. There could be some storage area for whatever activity happens here. You might have some building machine itself, which extends a bit and so on. So assembly line is a linear thing. There are nodes where things happen, and there are links which connect the line. And on either side of the line, depending on the station, there's certain amount of space required on either side. So that is the language we created. That is the grammar. Your whole design problem is now represented as a connection of, it's a network problem, connection of nodes connected through these links, and we have to solve for these nodes and links. So that is what we solved for. And these are just details of the user interface. So in 3 months, we created a platform which simplified the design problem. Now that was the details of how the buildings are designed. Now each building is connected to some other building, because whatever gets the output from here has to go in one of these buildings. So this is called a Voronoi diagram, which looks at, because in order to move the produce from one building to the other building, you need to move it either through forklift or through conveyor belt or something else. And it needs, if it is a forklift, for example, or a truck, it needs turning radius. So it accounts for all of that. And from there, even what you see here is that by distance measure, which is Voronoi model, it is creating the road network. So final layout looks something like this. You have the different building types, which each of them is a different processing unit within the paper factory. The output from one gets into the white line, show you the road network. So you can move things from here, take it to this building, here's the input, or you can move it from here, bring it here. The whole road network for the entire site, the building layout, all of that is generated by the computer not by the human user. So that's a good example of how AI could be leveraged, or computational thinking can be leveraged to solve complex problems within reasonable time. Right? Now that was about the paper mill. And because it's a petrochem sort of a platform, I also thought I'll show you one more example. This was the project we did recently for one of our Indian industry partners. We worked together with their team. So this is an organization which had got a project from oil and natural gas. And the problem was to design quickly design layout options, just like the paper mill, design layout options for the bed of the sea. In the bed of the sea, if you look at, this is how you typically take the oil. So in the bed of the sea, you have these oil wells. There are many details in how these oil wells function. And you have pipelines connecting these. You have these what are called PFSOs. PFSOs are floating units which collect all the oil and then take it to the shore. And all of these are connected to these pipelines. All of these details are to be designed. How do you create a platform which automates the design initially so that the designers can take that as the base and improve on the design further? So we started the same way as here, just the design grammar approach. But during this period, so this project happened in 22 to 24. During that period, what happened was LLMs also came in and other things. And generative AI also came in. So we also leveraged large language models to create a query-based generation of these designs. I'll not go into details, but what I'm again saying is the same problem, different representation of the problem, different ways to articulate the problem, and you can automate the design process, right? So that was about the design phase. Now, here's an example of a project done by a couple of my students in the MTech program, where they were looking at how do you use drones and machine learning to check for safety of scaffoldings. So during construction, you use these scaffoldings. Now, in these scaffoldings, sometimes accidents can happen if these scaffoldings are not correct or broken, or they're not tried properly, or they don't follow some standards, right? So what you'll see is the video where they created an algorithm, path planning algorithm first, which would follow the path to say how to scan the entire scaffolding given a particular project. And while it is the drone is flying, it will capture all the details and detect which of these connections are potential problem areas, right? So let me play the video and then we can have a follow-up after that. So on the bottom right, you are seeing the scan details. So it's checking for each of the joints and the members. Okay, I'll stop it here. Just to ask, how are you doing? Hello.
Hello, sir.
Yeah, how are we doing with time? Do we have time, or we are about to be over?
So we have a short time, sir.
Okay, I'll close it very quickly. Yeah. So essentially, in order to, if you want to really use AI and all of industrial IoT and all of that, it's also useful to understand how the computer-aided design has evolved in the industry over a period of time. I'll not go into details, but we started with manual drafting. We came to object-based models, solid models, and so on. And then now we are in the era of digital twin, cyber physical systems, generative AI. And hence, if you really want to do anything in the space of digital twin, cyber physical systems, generative AI, I'd highly encourage you to understand this history. Because if you understand this history, your basics will be in the right place to start developing the tools in the right way. So just to conclude, I have 8 or 9 things listed that if you want to develop any system based on AI or IoT or any of these things, there are 8 or 9 things we want to achieve in any project, whether it's petrochemical or whether it's any other smart factory or any other manufacturing sector. There are 9 things that we want to achieve, and these are the things you should think about. First of all, if I'm going to use any PLM system or information system How is it going to represent what I'm going to represent, even in digital twin? For example, does a digital twin always require a 3D model or not? It's worth asking the question. Why do you need a particular representation? Because the more complex the representation, the more cost you incur in maintaining the representation. Second question to ask is, what is the decision support I'm looking for? Am I looking for analysis? Am I looking for simulation? Am I looking to synthesize new ideas? What is the kind of decision I want to take with the solution that I want to develop? Third is that as part of the systems thinking, we are all part of a larger organization. So what is the right kind of information system which allows the team and the project teams within and with the clients and others to communicate, collaborate, and things to solve the problem? Solving the problem is in decision support. But in order to do that, you need to exchange ideas, exchange and communicate and collaborate. Eventually, if you are building a system, even if it's a digital twin or so on, you are managing knowledge and managing information. That information and knowledge has to be distributed and shared with everybody in the organization. How does your system allow you to do that? In order to do that, of course, you have to document. For many of these things, let's say if you are building a building today or a factory today or a design today to be executed tomorrow, you have to document it. Document so that somebody in the future can go back and check what was done and use it. The documentation is another important thing and hence important to think. Increasingly, things have become complex. We are in a world where we are talking about a lot of automation. So it's again worth thinking, what is the automation that you are seeking and what level of automation can be supported by your tool, the way you are developing. Finally, as the complexity has increased, it helps to have standardization at industry level, within the company, within the organization, within the team. There will be standardization at various levels. So what should that standard be? And of course, we are all part of a larger system. And hence, understand that if I'm going to develop a system or implement a system, is it going to be compatible with or be able to work with the systems that the others use in the industry or in other organizations? And finally, of course, as of now, we are still doing many of the systems for human users to be part of the system. So what is the experience of the human users? How do they interact with these systems become important? So these are the 9 things. If you can consider these things as your foundational way to think about whatever system you want to develop, it will help you develop better systems. With that, I'll stop here. I'll be happy to take questions. Thank you.
Thank you, sir. Sir, we have some question from participants.
Sure, please.
What is the first step for a traditional manufacturer who wants to start the digital transformation but has a limited budget?
First step for a manufacturer.
First step for a traditional manufacturer who want to start the digital transformation but has a limited budget.
Yeah, that's a very important question. I think the starting point, of course, is why do you want to do it? So objective, I already listed towards the end those 9 objectives, right? Do you want to do it just because everybody else is doing it? Or do you have a value proposition in mind? So you need to have clarity of the value that you want to seek out of the implementation. And the simplest solution is always the better solution. For example, I'll just give an example. So there are many companies, including SAP and Oracle, who have been developing software tools for people to use on construction sites. You know, the most commonly used information system on construction sites? It's WhatsApp. People exchange photos, every detail of buildings and all of that through WhatsApp because it's easy to use. So sometimes it's important to understand what is it that you want to achieve and only design for that. So that is the lean manufacturing sort of an approach, and I would encourage you to start from there.
Okay, sir. Thank you, sir. And one more question from audience. What are the key engineering criteria for optimizing riser and jumper configuration in ultra deep water field?
Okay, this is too specific for me to answer. I think the design team who worked on this would know. So I will not be able to answer this specific here.
Okay. Next, any other questions? Yes, sir. So one more last question. In next 10 years, will lights of factories with no humans be realistic, or we always need people in the loop?
Well, lights of factory are already there, including one in India. In China, there are many. There's a complete lights off factory in Hosur as well, one of them. I don't remember who has it. So lights off factory are a reality. There are lights off ports also. So in Vietnam, there's a port which has been run by Kone Cranes for the last 6-7 years with only one person just overseeing whether everything is working fine or not. So it's absolute reality.
Okay, sir. Thank you, sir.
Thank you very much. All right, if that's all,
As a
then
token of our appreciation for your insightful and engaging session, we would like to present the virtual certificate to you, sir. Thank you for sharing your valuable knowledge and expertise with us.
Thank you very much.
Thank you so much, sir.
Thank you.
Please join us at 1:30 sharp so that we can continue with the afternoon technical sessions. Thank you and have a lovely lunch break. So you can leave the platform and join back at 1:30.